Finish these off. All right, so for these, remember as we go across a row, let's see how you did. As we go across a row, atoms get smaller. As we go down a column, atoms get bigger. So as we go across a row, metals, which are trying to lose electrons, bigger atoms lose electrons better than smaller atoms. So potassium and calcium are in the same row. Calcium is to the right, so you would expect potassium to be a bigger atom, would be better at losing electrons. Calcium and magnesium, right, in the next slide, right? Calcium is lower down, therefore it's larger. Okay. Let's try the same for nonmetals. Remember, nonmetals are trying to gain electrons. So as we go to the right, atoms get smaller, should be easier to gain. As we go down a column, atoms get bigger, it should be harder to gain. So oxygen and nitrogen, try it on your own. I'll count to 5. Okay. And there you go. Oxygen is further to the left, not to the right, my bad. Oxygen is further to the left. No, I'm sorry, I was right. Oxygen is further to the right. It should be more reactive because it's smaller than nitrogen. I was just looking in the wrong place. Okay, fluorine and chlorine. Fluorine is higher up, therefore it should be a smaller atom. Smaller atoms gain electrons better. All right. Last thing we're going to do on this set of slides is talk a little bit about compounds and chemical bonds. Okay. All right. So atoms combine to form compounds. We talked about that with Dalton's hypothesis. By the way, even with Dalton's thing, one little thing, I don't remember if I mentioned it. If atoms are made of protons, neutrons, and electrons, how can we say that the atom is the smallest piece? And the reason is the protons, neutrons, and electrons are no longer the element. So the smallest piece of an atom that is still that atom is an element. Same thing with molecules, all right? So a molecule is the smallest piece of a compound, and though a molecule can be made from atoms, the molecule, the atom is not the molecule anymore, right? So atoms are held together by chemical bonds. Don't confuse bonds with intermolecular forces. So there's only a small number of slides here. All right, so bonds are between atoms within a molecule. If you break and form them, it's a chemical change, and you're making new stuff. We talked about that before. So these here are chemical bonds. Okay, and these are chemical bonds. The lines here are chemical bonds. And we'll talk about drawing stuff like this later on. So if I break these, it's making new stuff, right? Breaking and forming. Intermolecular forces are between molecules, and they're with what hold like ice together or water together. We talked about solids, liquids, and gases. So solids and liquids, the particles interact, right? Gases, they do not. The interactions between the particles are intermolecular forces, and we'll deal with this much later in the class. But if I break, that would be these guys here in between the molecules, right? So breaking those is a physical change. We're going to focus on chemical bonds. There's really two types, but one of them has a subtype. There are what are called ionic bonds, covalent bonds. I say purely covalent and polar covalent. We're really just going to go with ionic and covalent for now. We'll deal with polarity later, okay? But just for the sake of completion. So ionic bonds are the weakest of chemical bonds. They're between ions, okay? So you have positives and negatives. They have complete electron transfer. They're held together only by the fact that the positive ion sticks to the negative. Polar means it has positive and negative sides. Typically, it's between a metal and a nonmetal. So what happens is the metal loses an electron and the nonmetal gains it. The metal becomes positive, the nonmetal becomes negative. Okay, and they stick together. Purely covalent bonds are sharing of electrons. So if you look at something like chlorine, chlorine has 7 electrons and just wants 1 more. And it sees that the other chlorine has an electron, so it grabs on. You can't share something if you don't want it, so you can only share electrons in nonmetals. Okay, they're the strongest, so they're typically between 2 of the same. So chlorine, chlorine, oxygen, oxygen. Always nonmetals. And I'm talking about, we're going to talk about nonmetals first because we're going to deal with that stuff in the unit on air pollution and climate change and stuff like that. A lot of nonmetal chemistry. Polar covalent bonds are unequal sharing. So for example, if you look at between fluorine and chlorine, which one has the stronger attraction for electrons? Let me back up a couple slides here, sorry. Let's go back to this. All right, let me go to the whiteboard here. Find it. It's right here. So if we look at chlorine, let's back up. So chlorine, I'm just going to use a dot. Chlorine has 7 electrons, right? 1, 2, I'm just going to use dots to represent them. This is actually called Lewis dot structure. And we know it wants 8. Another chlorine also has 7 dots, right? 7 electrons in the valence. It's in column 17. And so this chlorine goes, oh, look, I just want 1 electron. There it is. Woo, yay. This chlorine goes, look, I just want 1 electron. There it is. But it can't pull it off because they're both chlorine. This, right here, that is the covalent bond. If we look at an ionic bond, if we have sodium, let's say sodium only has 1 dot and chlorine has 7 dots. We'll just use dots to represent the electrons. What happens in this case, this goes, oh good, I don't want it anyway. And so you end up with Na with no dots plus chlorine with 8 dots, which is what it wants, right? Everybody's happy. But it picked up an electron, so it's negative. So this sticking, that's an ionic bond. So that's what's going on. If we look at something between fluorine and chlorine, both of them have 7. So they're going to do the same thing, but because fluorine has a stronger attraction, it's going to pull these electrons just a little bit towards itself. And if you kind of looked at the electrons as a layer, you know, kind of thinking like a cloud, you get this kind of teardrop shape here, where we have a negative on this side and a positive. That is polar covalent because it's unequal sharing. If that confuses you, we'll spend more time on it later on. But just to get a feel for that, all right? So if the same nonmetal, they're covalent, 2 different nonmetals, it's going to be polar covalent. All right, just to summarize bonds in general, ionic bonds are between a metal and a nonmetal, ions, polar. We're not going to deal with compounds with this until much later, but it's a good time to talk about it. Polar covalent, 2 different nonmetals. I don't want to use the word electronegativity. Electronegativity is attraction for electrons. So the one that has the stronger attraction for electrons will be the negative side. Yeah, I stole this from another lecture. And purely covalent is 2 of the same nonmetal. All right, so this is just really quickly what you should get from all of these slides. Atomic structure, you should know the parts of the atom, which is the masses, charges, and locations. The arrangement, right, that's the locations. You should understand the difference between atoms, ions, and isotopes. From the periodic table, you should be able to identify metals and nonmetals. Using the table, you should be able to know how many valence electrons there are. The attraction for electrons, meaning here's a pair of atoms, what has a stronger attraction for electrons, and how does that affect reactivity? 2 metals, what's more reactive? 2 nonmetals, what's more reactive? And then we just finished talking about chemical bonds. All right, so that takes care of the slides on atomic structure. So that, it looks like it's 4 videos. It's a lot of slides though.